Welcome to the Deep Dive. We're your shortcut to getting quickly informed on pretty technical subjects. We take stacks of professional material, like today we've got electrician guides on control systems, dense stuff, and we pull out the core knowledge you need. So today we are plunging into, well, the hidden world of automated heating and cooling. It's complex, but it's everywhere. We're talking the logic, the physics, the mechanical genius behind keeping places comfortable, huge facilities, your living room, all of it. Our mission to really get a handle on the science and the controls that manage our comfort. Not just what the parts do, but why they're designed that way.
Yeah, it's crucial because, we're way beyond just throwing another log on the fire. These are sophisticated systems. They have
Yeah.
to balance comfort, safety, economy.
Yeah.
It's a lot. We're talking temperature, sure, but also humidity, air movement. It's quite intricate.
And we've got a great hook for this. We're going to figure out something I think everyone's felt. Why can you sometimes feel just plain cold, even when the thermostat is reading, say, a perfect 20 degrees Celsius? There's actually a term for it in the industry. Cold D20. We'll break down what causes that uncomfortable feeling.
Exactly. And understanding that, well, it starts with the basics, the physics. Heat fundamentally is just energy, molecules moving, colliding. It always flows from hotter things to colder things. Cold isn't really a thing in itself. It's just the relative absence of that heat energy.
Right. And that energy transfer, it's happening constantly and in three main ways. First is conduction, right?
Direct transfer through solids, like heat moving up a metal spoon you left in your coffee.
Okay, got it. Then there's convection.
That's heat moving through fluids, so air or water. You heat the fluid, it expands, gets less dense, and rises. Colder, denser fluid sinks to take its place. That circulation is key for furnaces, radiators, you name it.
And the third one, maybe the trickiest for comfort, is radiation. Heat moving as electromagnetic waves.
Like the sun's heat, or heat from a campfire. But importantly, we also lose heat through radiation. Our bodies radiate heat outwards.
Which brings us right back to that cold E20 feeling.
Exactly. See, human comfort isn't just about the air temperature number on the thermostat. Your body's constantly generating heat. Discomfort happens if you lose that heat too fast, or maybe not fast enough. The sources point to 4 key variables.
Okay, so that optimal 20 degrees Celsius temperature, that's just variable one. What else?
Humidity is huge. If air's too dry ideally, you want around 40% relative humidity at 20 degrees C. Moisture evaporates from your skin really quickly.
Yeah.
And evaporation cools you down, so low humidity makes you feel chilled, even if the air itself is technically warm.
Okay, that makes sense. What's number 3?
Air movement. Too much airflow, like a draft, strips heat and moisture away from your skin faster. Makes you feel colder.
Right, like sitting near a leaky window in winter. And the last one?
The fourth piece is radiation, like we mentioned. If you're near a very cold surface, like a big, poorly insulated window or wall, your body radiates its heat towards that cold surface. The bigger the temperature difference, the faster you lose heat. So you're literally losing body heat to the building itself, making you feel cold, even if the air thermometer says 20.
So cold E20 is basically when one or more of those other factors, humidity, air movement, radiation, are making you lose heat too fast, despite the air temperature.
Precisely. And the entire control system, everything we're about to discuss, is designed to try and manage all 4 of those variables.
Okay, so let's get into the components, the sensors, the system's eyes and ears, basically.
You've got 2 main types, generally speaking. Mechanical ones that often need to create physical movement or force, and then solid-state electronic ones, which are usually about high accuracy.
Let's start with mechanical. The sources talk a lot about bimetal devices. What's the principle there?
It's pretty ingenious, really. You take 2 different metals, weld them together into a strip or shape. Metals expand when heated, right? But different metals expand at different rates.
Okay.
So when the temperature changes, one metal expands or contracts more than the other, forcing the whole strip to bend or deflect. That gives you mechanical movement.
Clever. And how is that movement used?
Well, the simplest is the strip type. Just a straight strip that bends enough to open or close on electrical contact. Basic on-off.
Okay.
Then you've got the spiral type. It's wound into a coil. This gives you much more movement for the same temperature change. It winds tighter or unwinds. That bigger movement is good for things that need a bit more travel, like activating older mercury bulb switches.
And there's a disc type, too. Sounds different.
Yeah, the disc type is designed for snap action. It's shaped like a shallow dish. As it heats up, thermal expansion builds up stress radially until, bang, it suddenly snaps into the opposite curvature.
Like those little clicker toys.
Sort of, yeah. That quick snap is great for controlling larger electrical loads because it breaks the circuit decisively, reducing arcing. Good for fans, things monitoring airflow.
Wow. Okay, what about the bellows type? Sounds dramatic.
It is, kind of. Imagine a small sealed metal accordion. It's filled with a volatile fluid, often something like ether.
Ether. Okay.
When the temperature goes up, that liquid starts to vaporize inside the sealed bellows, turns into a gas, and gases exert pressure, a lot of pressure in this confined space. That pressure physically pushes the bellows, expanding it like an accordion.
Ah, so you get significant force and movement out of it.
Exactly. That makes it perfect for operating heavier switches, like the ones you find in line voltage thermostats controlling, say, big industrial unit heaters.
Okay, so those are the mechanical workhorses, but sometimes you need more precision than movement, right? Solid state.
Right. When accuracy is paramount, you move to electronics. Two main players here based on resistance changing with temperature.
First one mentioned is the thermistor,
Semiconductor device. It has a negative temperature coefficient,
meaning
meaning its electrical resistance goes down as the temperature goes up. Inverse relationship. They're small, cheap, pretty accurate for most HVAC stuff.
okay, negative coefficient, resistance down, temp up, got it. What's the other one?
For really high accuracy, like industrial processes, maybe controlling a furnace for refining metals, you use an RTD, resistance temperature detector.
RTD. Okay.
These usually use pure metals, often platinum.
Yeah.
Platinum has a positive temperature coefficient.
So resistance goes up as temperature goes up.
Exactly. Platinum is super stable chemically, very predictable. That makes RTDs incredibly accurate, the gold standard for precision thermal control in industry.
And briefly, they mentioned pyrometers for extreme heat.
Yeah, that's for non-contact measurement. Thousands of degrees Celsius, maybe on something that's moving. It's an optical device. It focuses the heat radiation coming off the object onto a very sensitive thermocouple sensor. Measures from a distance.
Fascinating. Okay, so all these sensors are feeding information. Where does it go? A thermostat. Command center.
Pretty much, yeah. The thermostat is the main user interface, but it's also where the switching happens based on the sensor input. The sources break down three main types of contacts inside thermostats.
Right. There are the mercury contacts, those little glass bulbs with mercury inside.
Yep, very common. Sealed, clean switching action as it tilts. But a couple of drawbacks, they can't handle really high electrical currents, and they must be installed perfectly level to work correctly. That's a big installation point.
Okay, what else?
Then you have the more robust, spring-activated, snap-action exposed contacts. These use mechanical force. A key feature is the wipe action. As the contacts make or break, they actually slide across each other slightly.
Oh, like self-cleaning.
Exactly. Helps clear off any dust or minor corrosion. Plus, the snap action minimizes arcsing. Good for higher current loads.
Makes sense. And the third type?
Glass enclosed magnet and armature contacts. These are also sealed, usually in an inert gas like nitrogen, which helps suppress arcs, similar to mercury bulbs. But instead of tilting, they're operated by a small electromagnet pulling an armature to make or break the circuit. Reliable for significant loads.
Okay, different contact types. Now, the logic. This seems critical. Heating versus cooling.
Absolutely crucial. They work in opposite ways. A heating thermostat needs to turn the heat on when it gets cold and off when it gets warm. So its contacts must close on a fall in temperature, make on fall, and open on a rise, break on rise.
Right. Close brings the heat on, open turns it off.
And a cooling thermostat is the exact opposite. It needs to turn the cooling on when it gets hot, so its contacts must close on a rise in temperature, make on rise, and open on a drop, break on drop.
Get that wiring wrong, and your AC runs when it's cold, and your heat runs when it's hot. Chaos.
Toggles chaos. Fights itself constantly.
Okay, and this leads us to, I think, the most ingenious part described, the anticipator. What problem does this solve?
It solves system lag, basically. Overshoot and undershoot.
Overshoot, like when the furnace shuts off, but the room keeps getting warmer for a bit because the furnace itself is still hot.
Exactly that. Residual heat. The anticipator is designed to, well, anticipate that and compensate.
How does it work for heating?
Okay, in a heating thermostat, the anticipator is a tiny resistor, a little heating element. It's wired in series with the thermostat contacts and whatever the thermostat controls, like the gas valve.
In series, okay.
So when the thermostat calls for heat and the contacts close, current flows through the gas valve and through this little anticipator heater. This tiny heater generates a small amount of heat right there inside the thermostat next to the bimetal sensor.
Ah, so it makes the thermostat think the room is slightly warmer than it actually is?
Precisely. It fools the thermostat into reaching its cutoff point a little bit early,
So the furnace shuts down before the room actually hits the target temperature.
allowing that residual heat from the furnace and ducts to coast the room temperature up perfectly to the set point without going over.
Hmm.
It prevents the overshoot.
That is really clever, but it sounds like it needs to be tuned.
Absolutely. If the anticipator is adjustable, its setting has to be matched exactly to the current draw of the specific gas valve or primary control it's operating. Remember, PIR, power heat, equals current squared times resistance. You need the right amount of fake heat based on the actual current flowing.
Okay, critical detail for setup. Now, what about cooling? Does it anticipate too?
It does, but in the opposite way, to prevent undershoot that lag before the cooling actually starts making you feel comfortable. The cooling anticipator is also a resistor, but it's wired in parallel with the thermostat contacts.
Parallel this time. Okay.
So when the cooling system is off, contacts are open.
Yeah.
A tiny bit of current can still flow through this parallel anticipator resistor. This generates a little heat inside the thermostat, making it sense the temperature rising slightly faster than the room actually is.
So it tricks the cooling system into starting a bit earlier.
Exactly. Gets a head start to combat that initial stuffy feeling before the cool air really takes effect. It's usually a high resistance, so not enough current flows to actually start the big cooling compressor, just enough to influence the sensor.
Wow. Series for heating, parallel for cooling. Simple components, but sophisticated logic.
It really is elegant engineering.
Now, installation. Location seems really important.
Hugely important. Needs to be on an inside wall, away from heat sources like lamps, direct sunlight, supply registers,
Wow.
anything that gives a false reading.
Makes sense.
But the sources stress something often overlooked. Drafts inside the wall cavity.
Inside the wall? How?
Yeah, if there are unsealed holes letting cold air drop down from the attic,
Yeah.
or warm air rise up from the basement inside the wall where the thermostat is mounted, that draft flowing over the back of the thermostat can completely throw off its reading. Those pathways need to be plugged with insulation or caulk.
That's a really good tip. Something most people wouldn't think of.
Definitely a pro tip from the manuals.
And quickly, before we hit safety, the sources mention programmable and two-stage thermostats, just briefly.
Sure. Programmable thermostats just automate temperature setbacks for energy savings. Cooler at night, warmer when you're home. Standard stuff now. Two-stage thermostats are for systems with, well, two levels of heating or cooling, like a high and low burner stage on a furnace. They use a second set of contacts to bring on that higher stage only when it's really cold or hot outside, more efficient and comfortable most of the time running on the lower stage.
Got it. Okay, let's shift gears to safety. This seems paramount, especially with gas appliances. The thermocouple.
Yes, the thermocouple is a classic safety device. Its main job in these systems is usually to prove that a pilot light is actually lit.
Found in furnaces, water heaters, that kind of thing.
Exactly. It's based on the Seebeck effect. You heat the junction of two dissimilar metals, and it generates a tiny electrical voltage.
Not tiny.
Very tiny. Typically around 30 millivolts DC for these pilot safety applications. But it's enough. That small DC voltage is used to power a small electromagnet in a safety valve or power unit. This electromagnet holds the gas valve open only as long as the thermocouple is hot from the pilot flame.
Ah, so it's self-powered in a way. If the pilot goes out,
If the pilot flame fails, the thermocouple cools down almost instantly. The voltage drops. The electromagnet loses its power, releases its armature, and snap, the main gas valve closes. Stops the flow of unburned gas.
critical safety function works even if the main house power is out.
That's a key benefit. Its main drawback, though, is that it's relatively slow compared to modern electronic flame sensors. A few seconds, maybe longer.
Okay. And because it's so critical, there are specific tests for it.
Absolutely. Technicians have to test them. There's the open circuit test. Disconnect the thermocouple and measure its millivolt output directly when heated by the pilot. Should be in a specific range, like 26 to 32 millivolts typically.
Measures its raw potential.
Then the closed circuit test. Measure the millivolts while it's connected and operating the safety valve. The reading will be lower because the valve coil draws power. Usually about 25% to 50% of the open circuit reading is considered good. Shows it can do the work.
Right, underload. Makes sense. What else?
The really crucial one is the response time test, or dropout test. You actually extinguish the pilot flame and time how long it takes for the safety valve to snap shut.
And there are strict limits on that time.
Yes, especially for larger systems. The sources get specific here about B2, which is British thermal units per hour, a measure of the furnace's heat output. For any large gas-fired system defined as being over 1 million B2, that's a big commercial or industrial unit, the safety shutoff must occur within 5 seconds of the flame failing, period. doesn't matter what type of gas. That's to prevent a dangerous buildup of unburnt fuel.
5 seconds, that's fast for such a critical failure.
It has to be. The potential hazard is much greater with that much fuel flow.
And there was one more test, only for gas fitters.
Right, the turn-down test. This is specialized. A certified gas fitter adjusts the pilot flame down to its absolute minimum stable point. Then they check if that tiny, weak pilot flame can still reliably and safely ignite the main burner when it comes on. Prevents delayed ignition or puffbacks. Needs expert judgment.
Okay, quite a thorough testing regime for such a seemingly simple device.
And safety demands it.
So we started this thinking about cold D20, that feeling of discomfort even at the right temperature. And we've seen it takes this whole integrated system understanding physics, using clever sensors like bimetals and bellows, precise electronics like RTDs, and smart logic like the anticipator just to manage those four factors. Temperature, humidity, air movement, and radiation.
It really is an interconnected system. All those pieces working together, constantly sensing and adjusting to maintain that comfortable, safe environment. Quite remarkable when you break it down.
Yeah.
And thinking about how carefully these systems try to manage those four cold D20 factors. It makes you wonder, doesn't it? For you listening, where might your own system be falling short? Is it maybe radiation loss through old windows causing that chill? Or is the humidity too low in winter? Might be worth investigating one of those factors in your own space this week.
Definitely food for thought. We hope this deep dive helps you see the hidden engineering working behind the scenes in your home or workplace. Thanks for joining.